Okay. So if you don't want any extraneous noises coming from your end, you can mute it yourself and unmute it as you want if you want to participate in any discussions or questions. Okay. I chose a different setting, and I'm sitting outdoors, which is actually on the top of my mother's house here in Bangalore. And so it's a different setting which has some plants, and it also has some laundry hanging in the back. So I thought it was a more airy look to it, but the light is kind of strong in my eye. So hopefully I can still see the slides as we are running through it. All right, so that's, so this is the setting we're gonna have for the next hour or so. All right. Do you have any? Yeah, I will discuss at the end issues about you know the projects and things like that. So we'll do that at the end after we finish the recording. Okay. So all right then, let's begin. We are still on this topic of applications of deep learning, and the topics here are. Computer vision is one of them, and we are right now discussing natural language applications. And we have had about 3 or 4 lectures on natural language. And this is the last of those lectures on natural language, and it is on the topic of attention models. And they have caught on in a big way in the last 2-3 years in almost every area of machine learning, saying when you endow your machine learning system with attention, it performs so much better. So not only is it a topic of importance to natural language processing, it is of importance to many other areas where you are endowing the deep learning system to figure out what to focus on, rather than give everything the same level of importance. It's just like looking at a computer vision, a screen in front of you. You don't give equal importance to every aspect of it. You're focusing on something. And how do we do that? And same thing in language also, when there's blah, 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 so much text going around. Certain words, certain concepts are what you need to be focusing on. So that is mainly the issue of attention. So what we're going to do is first we will define attention, and then we will talk about how attention was first used. The concept was used in the application of neural machine translation, how attention was used so that the right words were looked at when we are translating certain words, saying what is the concept, what is the context in which this word is being used. So we'll look at attention in the sequence to sequence area, and how attention was introduced in a particular paper about 5-6 years ago by Bahnadu. And that was the main paper which introduced the idea of attention in sequence to sequence mapping, that is like machine translation. And then came along a whole sequence of improvements, one called as a transformer. So originally there was a sequence, we'll begin with sequence to sequence, that is what is plain machine translation. And then we'll talk about machine translation with attention. So there are 2 different models. And the third one is transformer, which says, let's get rid of the RNN aspect of it, that is the recurrent neural network aspect of it, and parallelize the whole thing. So there is no sequentiality. And after that came a couple of more revolutionary systems developed by the Silicon Valley companies. One was Google's BERT, and the other one was the company called OpenAI, which is Elon Musk's AI company, and their product called GPT and GPT-2. All of them have some version of attention. So we're going to transition from simple concepts into some pretty sophisticated implementations involving large teams and so on. We just want to get a sense for what those revolutionary products available on the market today are. But anyway, let's begin with the first of the models, which is sequence to sequence in machine translation without attention. And let me just say that before we actually look at the slide, maybe it gets the concept in more clearly. In sequence to sequence models of machine translation, we are using an RNN to go from one word to the next word to the next word to the next word. And finally, we get some kind of a hidden representation, which being passed along from one word to the next word to the next word. The final hidden representation contains all the information given by the previous words, as well as the latest current word. And that is your essence of the summary of the context. And the RNN itself can be plain RNN with ordinary feed forward, or it could be those specialized ones we have seen, such as LSTM and GRU and so on. Doesn't matter. We simply refer to them as RNNs. And then that summary of all other information, it is some large vector. It doesn't even have to be large. In neural networks, we've seen that even a single number, which is 0 to 1, gives you an infinite set of representations. So you're using some vector, which is giving you what all went on earlier on. And that summary is being fed to the decoder, which takes that as the context, and it keeps generating words one after the other using the summary, and generates the first word, and then given what was generated as the first word and what the summary is, it generates the next word, and so on. That is the architecture of simple sequence to sequence machine translation. And then we move on to saying, look, it's just one vector that is capturing all that information of the past. And don't we want to give different kinds of importance to different words that have occurred in the past? You know, we don't want to treat them all as being equally important. And so how do we keep track of that? And that is where this idea of attention comes in, which says we're going to associate some weights with different words that have occurred in the past, and factor that in when we do the translation. We are going to take those weights, and now we do the same thing translation before, but there is a weight coming into picture. And then there is a issue of how do you determine the weights. And so there we use a neural network, a simple neural network, to figure out the weights. So that essentially becomes the idea of attention in deep learning. And then from there we go on saying, can we do something better in terms of replacing the sequential nature, because an RNN is still there with the attention model. Can't we get rid of the RNN part? And that leads to a very famous paper that was titled "Attention is All You Need." So they're getting rid of all the RNN part, and only the attention part is kept. And then we go on from there to the most sophisticated models. So I'm going to now enable these slides so we can go through what those are. Okay, so we have, let me put it on slideshow. Okay, here we are with the slides on attention models. It's available on the public site as well as on Piazza, which you all have access to. So this is just a summary of all the topics in natural language processing. We began with n-gram models, went on to neural language models, which was mostly about embeddings of words in neural space, and then dealing with high dimensional outputs, which is large vocabularies and so on. And then how neural language models can be combined with n-grams. And then specifically about neural machine translation is a topic we looked at last time. And the most sophisticated of those neural machine translation methods is attention models, which is our topic today. So we can begin by asking what is attention? And I think we all know this. You know, for example, like if a teacher says, "Can I have your attention, please?" Maybe somewhat annoyed teacher and saying, move away from all the conversations and other thinking you're doing, daydreaming you're doing, and please pay attention to what I'm saying. So that's the idea of, can I have your attention, please? So this is a common concept that all languages have a word for it. Attention in English, in Italian, it's attenzione. I don't know if any of you have been to Italy. You'll see these signs, police sign, polizei, attenzione, so warning. Or in German, you've seen it in World War II movies, there will be a Nazi guard on a World War II movie saying, Achtung, can't proceed any further, attention. The word for attention in French is again l'attention. And interestingly, Indian languages, in Kannada, the word for attention is gamana. And the very different words in different languages, showing that these are all it's a basic concept that every language has its own word. In Hindi, apparently it is dhyan, which is the word for attention. And there's a word in Tamil also, which my screen is obscuring for some reason. And okay, so it's the last word, covenant or something like that. So it means to focus on something and take note. So attention means to focus on something. All right. So rather than look at everything, if you have a scene, you're saying, don't look at everything in this scene. Focus on this little tree here, or a house here, or a person here. So it is paying greater attention to certain factors when processing the input. So it is just our intuitive idea of what we think of as attention. But the last sentence is an interesting one. It says, paying greater attention to certain factors when processing the input. So it is about figuring out what are the factors that when you process the input. For instance, we are trying to translate a particular word in a sentence, and which other words have a bearing on that particular word among all the possible choices, saying what is this word. So you have to keep in mind what is the context. You can think of it, context is a very general word. Attention is a more specific word about context. So I gave this example already last time. We'll look at it one more time. Attention vector in natural language processing. If we have a sentence, she is eating a green dash, and we want to predict what that last word is. And the choices could be any set of nouns. She's eating something, a green. So we could have, well, green qualifies what is that last noun. It could be apple, or a green could be some other object, a green tree, or a green plant, or a green chair, or something like that. So green will go along with that. So there is a certain degree of importance given between green and apple. We can say there is a degree of attention there between green and the last word. But there is a word eating which may have a higher attention, saying that is what is more influential in figuring out what this last word is, because it's about eating. So when we see the word eating, we expect a food word. Green describes food, but next word depends more on eating. So the attention for that word apple is more with eating than with green. So we're talking about a vector of some sort. So apple is preceded by, let's say, 1, 2, 3, 4, 5 words, and each of the words is a different level of importance. Eating has more importance than green. So we can say it's some number between 0 and 1, where eating gets a higher weight. So attention is a vector of importance weights. To predict a word in a sentence, we are estimating using the attention vector how strongly it is correlated or attends to other elements. So we're saying when we are predicting what that last word is, and we look at the attention vector and says eating is the one that has more importance. So this is all being formalized here. And in neural machine translation, for each output word, assign higher weights to relevant words in input. So here we are looking at English to French translation. So we have the English sentence, how was your day? And the French translation to that is, comment ça passe ta journée? Okay, so that is the translation. And this four-word input is associated with a four-dimensional vector. So these four words here, how was your day, is being associated. So there is a four-dimensional vector here, and the darker this one gives the key. Darker the element, it's more important. Lighter the key, it is less important. So here we are saying how is the most important word here, and then for the second word, how and was are important. And then for the third one, we have was is the important. And then here it is your is important. And then here it is a day that is important. So when we are making the translation or predicting what is this word, it is giving importance to the first word. And so that is what is going to influence this one. And then so on. And the last word is more influenced by day. And so this is a black box here, which has a number of things going on inside that big black box, some of which could be the embedding itself, which is first part is, which 300 dimensional embedding corresponds to how and was and so on. Those embeddings are now being mapped into some attention values. So there's embeddings and attention values. So attention values come from within this sentence here. And so you're not simply working with the embeddings, but also the relationship between the other words. That is what's going to determine what word it's going to generate. A decoder generates it. Of course, how does a neural network generate a word? That can be done by backpropagation, where we saw these methods of neural embeddings, where we can backpropagate in terms of a given word as output would be mapped into its own embedding. And then we could start figuring out what those embeddings are for the output words, and those can be learned. Just like in any other, for the input also, the output can also be learned. So there is one distinction that the attention folks make, and they talk about general attention and self-attention. So the attention component of a network manages and quantifies interdependence. So general attention is between the input and output elements. We just saw machine translation. We have some words in and we are generating some words out. So that's the general idea of attention. Self-attention is the earlier example we saw, where within a particular sentence itself, we are generating the attention for each words in that sentence. And that is all that is being used. And we're not looking beyond that sentence. And the general attention would look at the attention generated by previous text as well. So I'm just giving now here, because there is so much material in this attention, that we will study each of these to various levels of detail. One is the basic encoder-decoder RNN model, the recurrent neural network model. And we discuss it, without attention. What is the basic encoder-decoder model for machine translation, where this box called attention has not yet been put in? Attention came in as a more recent concept. Machine translation has been around for a long time. The idea of attention in neural networks is a more recent one. So we'll just look at what is the basic encoder-decoder model and what's lacking. And then the second topic is encoder-decoder recurrent neural network with attention brought in. And the third one is a transformer model with no recurrence. So we remove the recurrent part of it and say, here is another architecture which has got what's called multi-head attention, which means several different attentional modules simultaneously playing a role. And the fourth one is the generative pre-training of the attention model, which says you can train this transformer model using both supervised and unsupervised learning. So it's a mode of training of that. And that is it was a dramatic improvement, and that was developed by this company I mentioned, OpenAI, is the company that came up with this generative pre-training. It's called GPT, generative pre-training of attention model. And then there is BERT, which is Google's natural language processing engine. And this one got rid of the decoder part. The encoder-decoder is needed if you're going to be generating output words or doing machine translation. You need the decoder. And the BERT model that Google released was with no decoder. It was just a generative model to capture the knowledge about the language. And it can be used with whatever application you want. And the other innovation they put in BERT was to use bidirectionality. That is, why only look at sentences going from left to right? For instance, we had that sentence, she was eating a green dash, well, apple. Supposing the next sentence was, it was quite tart, some description of the taste of that apple. And then that kind of helps you figure out what that word is. The next one is about taste. And apples sometimes are tart, as opposed to something else. Maybe she was eating a green spinach or something. So those are so they are later context is also relevant, and BERT brought in this bidirectionality. So let's just first look at encoder-decoder without attention. So here we have the machine translation task. And the first box here is about translating from English to French. So the input sentence is, would you like coffee or tea? And so there's a sequence here. It's an RNN. It's processing these words one at a time. The embeddings of would you like coffee or tea. There are 300 dimensional vectors for each word. They're influencing one to the next, generating an embedded representation from one to the next. It could be an LSTM or a GRU that's doing that kind of processing. And so when we finish with looking at the word tea, it generates a vector, and in this case, it has generated a context vector, which happens to be of length 5. That's not particularly important. So it is a bunch of numbers, 0.1 minus 0.2, 0.8, 1.5 minus 0.3 is what the embedding is. You know, you can get any size of embedding you want by your architecture design. So it has brought it to that context, and that is capturing all the information that is contained in would you like coffee or tea? And that in turn is going on to the decoder, which is generating French now. The first word is voulez-vous du café ou du thé, is the French translation of encoder to a decoder. And now we point out and saying, wow, that is, what a summary, you know, 0.1 minus 0.2, 0.8, 1.5 minus 0.3. It is capturing all that information and allowing us to generate a sentence like that. Let's, you know, and that's where we say we could do better than that. It doesn't show the importance of the previous words and so on. And the box below, I just made another example, which makes another point. This is translating from English to Kannada. The input sentence is, would you like coffee or tea? And the context vector is the same as from English to French. So in a sense, that context vector is like an interlingua. It is some kind of, the concepts in that sentence are all embedded. So there is an embedding, just like there is an embedding for a word, that is an embedding for a sentence. So the concept of would you like coffee or tea is embedded in that. So the surface output representation has to be in Kannada. And those of you who know Kannada can read the Kannada, or you can read it in English below. It says, Neevu kafi athava chaha bayasuvira. Right? So that is the translation from English to Kannada. But the context vector, whether we're translating it into French or into English, interestingly, are the same. And the outputs are generated using backprop, as we talked about earlier on, so that it generates the right words. So let us look at more of the roles of the encoder and decoder in neural machine translation. This is again the example of English to French. So the encoder compresses the input sequence into a context vector. So we can say, what is this context vector? It's a sentence embedding, just like we know what word embeddings are. Or it is a thought vector of a fixed length. So it is some kind of a thought vector. That is the thought. It is expected to be a good summary of the meaning of the whole sequence. So that is what is going on. And the decoder is initialized with the context vector to emit the transformed output. So we saw that earlier on. So that is the role of the encoder in the decoder. This is a nice diagram of the basic encoder-decoder architecture, giving a little bit of more of notation and terminology. This comes out of a new book that's coming out by Jurafsky and Martin, Speech and Language Processing. And it's available online, but the book is not complete. Only certain chapters are available. I think it might be coming out later this year, but it's a nice summary of all aspects of natural language processing. But we are only interested here in these attention models. So they kind of begin again with this basic RNN-based encoder-decoder. It's the same diagram we saw earlier on, gives a little bit more detail and terminology. So let's see, we have an encoder RNN here and there's a decoder RNN here. The encoder RNN begins with the words, whatever be the sentence we have, right? Would you like coffee or tea would be these words. And what is shown up here are the word embeddings. So this word has been mapped into, starting with a one hot vector. We begin with a vocabulary of 100,000 words or 10,000 words, and that's mapped into a 300-dimensional vector, some of which are on, some of which are off, and so on, if it is binary. And that's an embedding, it's an embedding. So these embeddings are what go into a representation that we are generating. And we have this notation H1 of E, H2 of E to Hn of E. E stands for encoder. And the length of the input string is N. So we are generating a string of hidden representations. But all that matters is the last hidden representation, Hn of E. That's all that is being used. And all of it, the earlier ones go on influencing what that's going to be. And that is all the summary of this input sentence is being passed along to the decoder RNN. The decoder RNN has value, generates outputs H1 of D, H2 of D through Hm of D. So the output length can be different than the input length. And what is happening is each of these units here are producing a different set of possible values for the output Y1. Like the first one just has the context coming in, whatever was output here. And this bar chart here shows that it gives you a preference among the vocabulary as to which word is most preferred compared to other words. And so it is choosing, in a way, this is softmax here. So this is called softmax outputs, which is all the probabilities associated with the entire vocabulary. And we can say, well, there is the most likely word of the softmax, and we say that is the output. And that output is being fed back into the next stage that is taking into account what was generated by the previous stage here. And that, as well as the output, are being used to generate softmax for the next one, next one, next one, and so on. So essentially, this is how a basic RNN-based encoder-decoder machine translation engine would work. And of course, that is how they were implemented, and they were state of the art at some point. But yeah, as in all of deep learning, slowly they started replacing the original methods with deep learning methods. And here is an understanding of a simple deep learning approach to solve the problem of machine translation. And the final encoder of the hidden state HNE serves as a context for the decoder. We just saw that. And both the encoder and decoder are RNNs. These are all, it's a recurrent neural network. And they could all be units that are LSTM or GRU, which are a little bit more sophisticated than plain feed-forward networks. This slide again gives the same thing reinforces the notation sequence to sequence RNN. We have an encoder and a decoder. Encoder encodes the input sequence into fixed length vectors, and decoder takes a single fixed length vector as input and generates the output. And the main point of this particular slide is the word auto regression. So we say that this encoder decoder uses auto regression. And what does that mean? It consumes the previous output. So generating the Y2 consumes Y1, the previous output, as well as this encoding of all the input information that's being fed here. So that is what's going on in the encoder-decoder model. So this is the basic encoder-decoder model. It has not used the concept of attention as yet. So this again is a nice diagram that Jurafsky and Martin, I believe they're at Stanford, which is the preeminent group in natural language processing. And they're the ones who invented this idea of attention, which is influencing all of deep learning. So anyway, this is another diagram which says, here is a summary. X1 through Xn is the input, there's an encoder. Y1 through Ym are the outputs, there is a decoder that generates them. And the encoder and decoder are connected through a context mechanism, which is summarizing all the information that has gone on. And what does this slide say? It says simple RNNs, LSTMs, GRUs, even convolutional neural networks, and it could also be transformer networks. We'll see what those are. And only a single network layer is shown. There could be several layers, encoder, encoder, encoder. In a stacked architecture, output states from the top layer is taken as a final representation. So you can go from words to next level to one more level, just like we have seen in CNNs. We can have several levels of processing, which is summarizing the information well. And you are hearing some truck traffic on the street below me. And so there's not that much traffic in Bangalore, but there is an occasional one. And let's see, move on. And a widely used encoder design makes use of stacked bi-LSTMs. So it could be LSTMs going both ways. And the decoder is autoregressive. We just saw what autoregressive is. That is, the previous output is consumed to generate the next output. And an element at a time until the end of sequence marker is generated. And this incremental process is guided by the context provided by the encoder, as well as any items generated for earlier states by the decoder. And again, a typical approach is to use LSTM or GRU-based RNN. So this is the summary of the encoder-decoder model. So what is a deficiency of the traditional encoder-decoder? The truck is going fast again. They blocked off the road and the truck driver couldn't go any forward. So they don't want to have traffic, and this truck guy was trying to go by. Okay, so the encoder compresses all input into a single fixed length vector h sub n to be passed to the decoder. And it is saying it's got a single fixed length vector. We just saw that fixed length vector is a summary of all the information. It leads to loss of information. And it's unable to model alignment between input and output sequences. So which word is aligned with which word and so on, that is maybe a value. And it is essential for structured output tasks such as translation or summarization. So we consumed, we given a position to each word and so on. Keeping track of that is not done properly by the sequence to sequence mapping. So the intuition of what is needed.
I have a doubt.
Yeah.
So in LSTM or RNN, we do use of the sequence, right? We feed the input in a sequence. So we are considering the alignment.
Yeah, it is kind of summarizing all of it. And it is not giving any importance to which word generated what. Just think of the basic idea of a word embedding. you're taking a word as input and generating a 300-dimensional vector. And of course, you did some kind of a learning mechanism to do that, supervised learning, to figure out what should be the 300-dimensional vector. But it is just going, in where it is used, and based on that, it is just giving a representation. There is just that particular words concept is getting mapped. Similarly, a sentence is getting mapped here into an embedding, and it is not explicitly keeping track, saying, well, what is the contribution of word number 1, word number 2, word number 3, word number 4. It's kind of getting lost in that mapping process. And the attention is saying, we need to keep track of that. We need to keep track of which word influences what. And then we go on to this attention model, which says, the robot must behave itself, all right? Supposing you had something like that. And what does itself refer to? Itself refers to robot. And so we need to have that kind of, rather than have the whole concept translated, it says itself refers to robot, and that information should be explicitly captured, is the idea. So there is no proper indexing. That's all it is. Have we indexed this word, and what is its importance? And when we're generating the translation, what is it referring to? Itself is a mentioning of the robot here. And so, and rather than the whole thing, you need to say that particular word. And we use what are called masks also, which says, okay, certain words are not important. Certain other words are extremely important for the next word. She's eating a green apple. That word eating is important, more important than the word green. And that is the relative importance is what attention is saying you must capture. Whereas the previous methods, LSTM and so on, they're kind of giving you a gist of the whole thing, and not giving you an indexing mechanism. So you can think of it as a mundane thing. The attention, all it is saying is, same thing, you got to have the concept all represented just like an embedding, but have a mechanism to index these words, because future words may rely on the importance of those words explicitly, right? Okay, so that's what it's saying. So I guess that's being said in this slide. In sequence-to-sequence task, each output token is expected to be more influenced by some specific parts of the input sentence and not by the whole thing. So, and also there is one more thing that is lacking in the sequence-to-sequence model is that the decoder lacks any mechanism to selectively focus on relevant input tokens while generating each output token. So I guess those are related topics. So it is saying that which are the input tokens to focus on while we are input words to focus on while generating an output word. And so there is going to be what's called as a attention value, alpha ij. The alpha ij is going to be the importance of the ith word in generating the jth word, ith word of the input to the jth word of the output. And there is some kind of a vector coming into play. So there will be a vector of alpha ij's coming in, which are generated by the vector of associated with the input sentence, and which leads to learning the alpha ij's, right? So that's the intuition here. So, okay, right now all we have talked about is the basic encoder-decoder RNN model without attention. Now we go on to, okay, how are we going to do it? Encoder-decoder RNN with attention is the next topic. So I thought it's nice to put the block diagrams of the encoder-decoder without attention and the block diagram of the encoder-decoder with attention side by side. These are two different figures in the Jurafsky Martin book, but I thought I'd place them one next to the other. It kind of helps us to see what is so different about the attention vector. So the previous one we just saw already was the encoder-decoder without attention, which just has some vector, context vector. Attention model says, well, we got the same thing here, x1 through xn. This is also an RNN, same process. Instead of a single vector here, there is now this C sub I, and it is running through different words of the input here. There's a context here. And and that is what is fed to the output. So we are now dealing with C sub I, and where C sub I is a summation of alpha ij hj of e. Okay, alpha ij. So that is now relating the I and j. I corresponds to the input, j corresponds to the output. This alpha is the weightage, and the weightage is multiplying hj of e, which takes the corresponding weight vector here. Okay, and this is running through all these. Okay, the context I already related to the output. Now that j corresponds not to the output, but we are running through all of these hidden values here. So the influence of each of the words is obtained by the alpha ij's multiplying the HJFE. These are the HJF, the encoder here. There's a weight associated with it. And together that gives you a particular value. It is just a weighted sum. We've seen these kinds of equations before. That's a linear, linear function of the inputs of the vectors HJFE. And you can imagine HJFE are vectors. And these vectors are multiplied by a scalar alpha ij that's creating another vector over here. So the Ci is a vector. And what are these alpha ij's? The alpha ij's is obtained by doing a softmax of the h's that are coming up here. So those are being used. We saw the role of the softmax function here, which ranks all the possible values. Right? And so now we are getting something more elaborate going out. So it is not just a vector, but we have now a set of vectors C sub I, which have somehow absorbed the attention values. So the hidden values of all the words. Previously, we didn't have all the H's coming in. Now we are getting all the hidden values, the embeddings coming into play here. And there are context values associated with every one of the input words. These are context vectors, which have got different kinds of weightings associated with the inputs. So that is what this CI is. So that is now what is, this context is what is being fed over here for the next processing output. And that is being influenced by the previous one and the context for that particular word. And that is also consuming the particular previous output here to again do the same task. So it's a bit more sophisticated, where the importance weights alpha ij are being brought into play. So this gives a more detail now. Let's now take a closer look at the encoder-decoder with attention. And I put the same diagram up as the previous one. Previously, I just juxtapose the with and without attention. Now we got attention in this model. There is an encoder hidden state, HJFE. There is a decoder hidden state, HI of D here. All right, so that is these values. And so the decoder hidden state, HI of D, is based on the previous hidden state, previous word generated, and the current context vector, CI. So HI of D, decoder, is a function of the previous value of y of hi minus, the previous h here, hi minus 1. And it's also a function of c. So this is focusing on this box here. Hi of d is a function of yi minus 1, hi minus 1 of d, and ci. So it is just stating it mathematically, the same arrows here. And the context vector ci, okay, I guess this CI is actually corresponding to this HI, right? So that is, and that CI is alpha ij. So it does correspond to the combination of the input and output. And Hj is purely about these with the encoder. Okay, so Hj is about the encoder. Alpha ij is between the encoder and decoder. Ci is the output here corresponding to the ith output here. So it is the context vector Ci is obtained by comparing the previous hidden state. So we saw that equation already. Ci is this equation. And then it's alpha ij. So how is that alpha ij determined? That's what these equations at the bottom here. It says the alpha ij is a softmax of a score of hi minus 1 and hj. Softmax, if you recall, all it is an exponential of that value divided by summation of exponential of all the output values. So softmax makes sure that the values all add up to 1. So alpha ij add up to 1 when you're running over all the values of j here. So it is based on a score. And what is a score? Score is defined over here. There are many definitions of score. One is called the dot product score. The other one is a general weight matrix. Those are two popular ones. There are like a half a dozen ones in one of my tables coming up. So this is a score. A score is between hi minus 1d and hjfe. So this is relating the I values from coming up and the j values. And we have, in this case, hi minus 1 of the decoder. Okay, so there is the decoder value, and then hj is of the encoder value. So there is an encoder value here, and then there's a decoder value. So it is relating both of them. So this is saying the score is nothing but take the two hidden unit vectors, multiply them as a dot product or a scalar product. Another one says, well, you could multiply them with a general weight matrix in between them to obtain a scalar value, which is the score. And the scores are all being processed. That's what this definition of score, which gives us the alpha ij. And so the context vector for output yi and alpha ij is how well two words yi and xj are aligned. So this is called as an alignment matrix alpha ij, is showing the alignment between the input words and the output words is being shown by the alignment vector. And that alignment vector in turn is based on a neural network output, which is a softmax output. And there is some multiplication, vector multiplication going on. So this is all that is happening. So we have a neural network figuring out the alpha ij's in between. And a later diagram here shows that neural network. But there is one slight add-on here before we look at that neural network that figures out the alpha ij's, that bidirectionality is considered as an important concept. And how do you get bidirectionality in? It's extremely trivial. To get bidirectionality, when you have an input string x1 through xn, we have the h's generated from left to right on the top, and then from right to left at the bottom. And when you have two h's, the combined h is given by the left to right h and the right to left h. Together forms the hidden unit vector for that input. And then here are all the global alignment weights here between the input and output. And the decoder generates the output. So this is just about bidirectionality. And this, in a lot of the next slide after this, I'll show you a TensorFlow version of this that is available. And these TensorFlow versions for machine translation, they generate the alpha ij matrix, which is kind of interesting to look at. Here is a matrix of alignment scores. The input sentence, let's just read English rather than French. The agreement of the European Economic Area was signed in August 1992, end of sentence marker. And in this case, I believe it was French to English rather than English to French. So the French was this sentence, l'accord sur la zone économique européenne était signé en 1992. So this is the English input, and this is that's the French input, and this is the English output. This is a matrix here, which consists of alpha ij. Ij are simply the indices for the input string and the output string. And those alphas, we made sure they were all values between 0 and 1 by making them softmax values. And this shows the strength of the alignment between the input and output. For some words, they go beyond the diagonal. Diagonal means exactly the corresponding word. The values going outside the diagonal means there is some uh, some uh, um, uh, some words which are not exactly in that same position can be of importance in the translation. And this has been a pretty active area of research. And there are what are called as context-based attention, additive attention, local-based attention, general attention, dot product attention, scale dot product attention. And a bunch of papers starting about 5 years ago. And this was the paper that was won in 2017, was that attention is all you need, which says they get rid of the RNN structure, which gets into what's called a transformer. That paper is about transformer. But the most important paper was this Bardano paper. There's a variation of it called the Luong version of it. All the variations are that Bardano was about the score is they're using a weight matrix here, and then there is a location base was the Bardano. And you can hear some loudspeakers on the roads of Bangalore urging people to stay indoors. So all this is happening when you're outside. You can hear issues about related to COVID-19 here in India. All right, then. So these are all the different scores. Self-attention seems to crop up again and again when you're studying attention. Self-attention is also known as intra-attention. It relates different positions of a single sequence to computer representing the same sequence. So it is obtaining some kind of a representation of this sequence and saying what is the relative importance of word to word apple of green and eating, self-attention. Relating different positions of the same input sequence. Theoretically, the self-attention can adopt any score functions above, but replace their target sequence with the same input sequence. So it is not just for machine translation, but figuring out what is the influence of words within a sentence. And there are other variations, global, and then there is also local and so on. So pretty active area of research. So this part I found it interesting is, okay, alpha IJs, that's what were displayed. You can show the matrix, how do the words line up? But who figures out what the value of alpha IJ is? It's a value between 0 and 1, that much we know. This slide gives you a little bit more on that. Alpha IJ, they capture the relevance between the decoder hidden state HID and the encoder hidden state HAE. The corresponding words, we are looking at not the tokens, but the embeddings. What is the relevance between the two? And these alpha IJ are what are used to build the context vector CI at each decoding position I. So that we saw already. CI are used by this equation in the middle of the slide. It's saying how alpha IJ are used. And this diagram here gives you a sense for how that could be done. This is a neural network here, a deep learning network, whose inputs are the HIDs and then the HIEs. There's the decoder and there's the encoder. And for every combination of the decoder and encoder, it is learning a value of alpha. So alpha 1, 1, and so on. So a neural network takes the values of HIs, look at the arrow going in here, and it also takes the value here. Together, it learns the values of alpha I in the training phase. So in the training phase, the alpha I, so you would have had text that is English and French, and you've been training it on that. The English words and the French words together go about telling you what the values of the alphas are. And then once you learn those alphas are what are used to generate, like when we're generating H2 of D as Y2. C2 is alpha 2 1 H1 Fe plus alpha 2 2 H2. The corresponding alphas are being used over all the hidden values here to generate this. So the main point here on this slide was a neural network is what is used to generate the values based on the training text. This is the blog I found, and it is tensorflow.org tutorials for neural machine translation with attention. And so you can just go to this site. I've given you the link here. You can run in Google Colab or view source in GitHub and download the code. And it gives you some diagrams saying what is happening. You're translating, I am a student is English, and the French is je suis étudiant would be a French. And this translation takes into account this input. And in the training part, it's taking the output. And it is learning attention weights from all of these. And from the attention weights, it's figuring out the context vector. From that, it's giving the attention vector to be able to generate that sentence, which is the translation. So it's showing the diagram. And the TensorFlow code shows how you can generate a plot of attention weights. This is translating English to French, and what is the attention weight. This is my life in English, and this is the equivalent in French. And it's showing corresponding importance of these weights. And it shows for this particular code, the alphas are being computed with softmax. CIs are computed exactly the way we described. And the ATs, the attention values, the attention vector is a tan H. So the attention values, the neural network we just saw in the previous slide, using it generates attention vector. And the score, they give two different equations. You can choose between Luong's multiplicative score or Bahdanou's additive style and so on. So this is all that's going on in the main model. And then there is two more models, which I will wrap up rather quickly. They're pretty complex: generative GPT and BERT, which are state-of-the-art methods, pre-trained and so on. They're just offering it to you. GPT is interesting. GPT, they're both based on the idea called transformer. I think we should spend a little time on transformer before I go to GPT and BERT. So a transformer is an attention mechanism to learn contextual relationship between words. It includes, again, two mechanisms, encoder and a decoder. But the model has no recurrence. So it says, we need an encoder and a decoder, but we don't need a recurrence like the LSTM and GRU or plain recurrent neural network. This one says we can directly do that, and a transformer is done that. This was the paper, Vaswani's paper on attention is all you need. And it has an encoder-decoder architecture, and it's a stack of encoders here. Okay, so that is something very straightforward, and the stack of decoders. So the encoder maps input x1 x through xn to z1 through zn. Given z, so this is a full sequence of embeddings, and the decoder generates element-wise outputs. And each step model is autoregressive, and just autoregressive, we saw that. So it's some stack of encoders and decoders. And this diagram looks pretty complicated for the transformer. This is the transformer diagram. It's got an encoder part, which is the left part here, which is the decoder part, which is the right part here. And it says multi-head attention, masked multi-head attention. Multi-head attention simply means that there are in parallel several attention mechanisms going on. And each of them does slightly different things. And same thing, masked means you're masking some words, and there is some kind of specialized training going on where you're not looking at all the words at the same time. Autoregressive means it consumes previously generated output. So what's happening is input embedding. There's some coding, a positional encoding where the words are occurring. There is multi-head attention, and there is some kind of addition of the results, normalization, a feed-forward network, addition and normalization. That is the encoding part. Goes into the decoding part, which is the output shifted right during training part. Otherwise, we are directly going to generate the output, and so on. Okay, so that's transformer. So we just saw this diagram of a stacked encoder-decoder, input to output. And this slide is giving a little bit more about self-attention. And it gives you an example. Here is the English sentence. Second law of robotics. A robot must satisfy the orders given it by human beings, except when such orders would conflict with the first law. It says, what is this it? It refers to robot. Such orders refers to the earlier part, which says must obey the orders given to it by human beings, and would conflict with first law. What is first law? First law is something refers to an entire first law, which is before the second law of robotics. So these are the kind of self-referential things happening in a sentence, which is self-attention goes about figuring out what do these things refer to, and it bakes in the model's understanding of relevant words and associated words that explain the context of certain words before processing that word. So before we start translating it or such orders, it knows that there is certain importance of the connection between such orders and these orders and it and robot. And self-attention is saying even within a sentence, there are all these dependencies. And so it's defining self-attention. And there is some terminology here. If you really want to get into this, there's talk about query, key, and value, how words are processed, and it gives you illustrates the concept. Consider the sentence: a robot must obey the orders given it. And the masked self-attention is saying it depends on a and robot, and it says there is a certain weightage associated with between dependency of it and a and robot. And how do you organize all of this? So it is not just a simple vector, but so you have to have some kind of a filing scheme saying it has refers to a key here, and this is a three-dimensional vector. These are three masked words here, and it is being related to all the words and all the strengths, like 50%, 30% correspond to a and robot. So it shows words, value vector for the words, and the scores, and the value times score. It gives you all kinds of detail about the bookkeeping. Let me just say that that's what it's all about. The self-attention process is to keep track of which word influences which other word. So you have a data lookup issue here. So the kind of stuff information retrieval people do is how do I get the particular importance of which word? And they have an elaborate scheme based on query, key, and value. And this is a full transformer with attention. They're expanding this little piece with a selected dot product attention and all that part, the magnification of this one. And this one has another magnification of the scale dot product attention. So this is a whole product, there's a whole parallelism of all these scale dot products. And all of that together are coming to play. And these slides here give a little bit more detail of the transformer encoder detail, and then the transformer decoder detail, and more detail on the query, key, and value. Why do they refer to them as query, key, and value, which is interesting? Query is to compute next word in a translation. Query is, okay, I need to get the next word in the translation. And so the attention mechanism creates a vector using the source sentence and what has been generated so far. So it's as if like you're in an information retrieval phenomenon. We're saying, what is the next word? Well, it says you got to go and look up. As if you're doing an information retrieval. That's what we do. When we do a Google search, we're putting in a query, and it goes and looks up all the knowledge there is and comes back to you telling what is the answer to your query. Just like that, they are going about it here as if there is a query and key and value. Value is what we get out of it, and key is the indexing scheme that is being used. And so there is more stuff here about these ideas of query, key, and value, if you're so interested in looking at this kind of detail. And a little bit more on the scaled dot product attention and the detail of the multi-head attention. There's a concatenation of all of these different attention models, so on. So that was the phenomenal paper on attention is all you need. It says it got rid of recurrence, but is looking at the whole input. And then goes on to this OpenAI's work on generative pre-training of it. So now, so the people build on top of each other's work. We went from RNN model to RNN with attention. And then we have the transformer model, which got rid of the RNN, but just kept its attention part. And then we go on to an improvement on the attention model by generative pre-training. What does that mean? It means the pre-training using a generative approach. Generative models are those that it's unsupervised learning. It says just look at this data and give me a representation of the distribution of this data. So that's exactly what they're doing here, is to look at a lot of text, learn from all of it, and they're providing pre-training and saying this attention model that you've got for translating and all that can be helped by throwing in knowledge of English from all over the world. So they throw in billions of words of text from different sources in this OpenAI project. It's an Elon Musk company, OpenAI. And so they said, wow, it performs so much better, almost human-like performance in translation. And then came along Google's group BERT. They said, let's improve this GPT even more by introducing bidirectionality into it, which these guys didn't do. And that became even better. So you have all kinds of pre-training going in. And they also dispensed with the decoder, saying we just need a generative model for English or whatever language. So this says though the two improvements over transformer were the OpenAI's GPT and Google's BERT. And here is a screenshot from GPT-2. So a GPT became GPT-2, and you can take a look at their websites. GPT-2. I think I showed this example way earlier on with NLP. The cat sat on the. That seems like a simple enough task. It says floor with 8.4%, so on, and then a window with 1.2%, and I guess floor is the most likely word for the cat sat on there. But bed is the second one with 7.3%, 5.6% is couch, and so on. So it's all indoors. I guess it's appropriate for these times, right? Anyway, so while trying to predict the next word, this is a simple task. I give you a sentence, the cat sat on the, predict the next word. So that's how they trained it. Surprisingly, it learned basic competence in tasks like machine translation, question answering, even without ever being told. And it was interesting that OpenAI, when they released this GPT-2, they said, this is too good. Too good in the sense it can generate such text that are totally believable and not even done by any human being. It's kind of dangerous to have text that is generatable, which are better than human beings. And the next one gives you this example, which I mentioned once in class. So you have a system prompt, which is human written. The system prompt was some kind of a nonsensical writing. In a shocking finding, scientists discovered that a herd of unicorns living in a remote, unexplored valley in the Andes Mountains. Even more surprising to researchers was the fact that the unicorns spoke perfect English. So it was as if there was this non-existent animal herd existed in the Andes. And not only that, they all spoke perfect English. And they gave it to this GPT-2 to generate new text. And this is what it generated after 10 tries. I guess it kept on improving it. The scientist named the population after the distinctive horn Ovid's unicorn. 4-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. It's giving a name. Dr. Jorge Perez, an evolutionary biologist from University of La Paz, noticed that the valley had what appeared to be natural fountains surrounded by two peaks of rock and silver snow. Perez and others further ventured into the valley. By the time we reached the top of one peak, the water looked blue with some crystals on top, said Perez. Perez and his friends were astonished to see the unicorn herd. These creatures could be seen from the air without having to move too much to see them. They were so close they could touch their horn. All of it generated by this OpenAI, which has learned English from lots of writing, and it is able to write these kinds of English. So this is what OpenAI was saying. We don't want to release this text; it is too good. It can generate all kinds of nonsensical paragraphs and sentences and news and whatnot. Anyway, that is about GPT, and it's kind of how they trained it is interesting. Architecture of GPT, it involves tasks such as unsupervised learning and supervised learning. Supervised learning would be task classifier. Right? That's saying, okay, you're saying, is this the correct word or not in translation, for example. Unsupervised learning is to predict text, is what's the next word based on frequencies and so on. So both of them are coming into play in the same architecture. There's a little bit more detail here about how unsupervised learning and supervised learning can coexist in this GPT, and how they dealt with different tasks in natural language processing, classification, entailment, which is the kind of project you're doing on project 3, which is about figuring out whether another passage of text follows from the current passage or not, and similarity and multiple choice and so on. And the last part is BERT. And in BERT, it uses a transformer attention mechanism, and it just generates the decoder, the encoder, not the decoder. And it uses masked language model to allow bidirectional training. And I think I have a slide or two about what is this masked training. Certain words are masked off and we generate. What is the training? They trained on 800 million words. Wikipedia of 2,500 million words. I guess the entire Wikipedia was digested. And again, a book corpus of 800 million words and so on. And they're pre-trained model for 102 languages. So they've covered everything. So basically, there's a powerful model called BERT that exists. So for any NLP work you want to do, all of this is all readily available. All we were learning was how could this have been trained, and what led to this kind of model is what all our discussion has been about. But today, the state of the art is extremely good. And there is some comparison of BERT and OpenAI and another thing called Elmo. What are the differences between all these models? And what is this masked learning? So on. BERT is pre-trained on 2 NLP tasks: masked language modeling for bidirectionality, next sentence prediction, and so on. I have a few slides on what is masked language model, which is before feeding word sequences, 15% of the words in each sequence are replaced with a mask. And they try to predict those words. So that's an interesting task. That is, you have the sentences where you don't show certain words and train it to learn those words. Okay, how well it did. So you want to, that's a supervised learning problem, which is called masked learning. And this shows masked learning about sentences, how you're masking different words. I'll leave it to you, take a look at these things. Next sentence prediction. And the software available, you got BERT base, BERT large, and BERT base has 110 million parameters, 12 attention heads, 12 layers, transformer blocks. BERT large is 24 layers, 16 attention heads, 340 million parameters. So I'll conclude our discussion of both attention models and natural language processing. That attention has revolutionized natural language processing. It's now a standard fixture for NLP. And because it enables a model to remember all words in the input and focus on specific words when formulating a response. That's what attention brought to the picture. Early models were sequence-to-sequence models with RNNs, and recent ones include self-attention and transformer models. And Google's BERT, OpenAI's GPT, and XLNet are the most popular ones today. They're based on self-attention and transformer. Okay, so I'll stop there. And okay, so if you have questions other than project due dates and so on, you can ask now, and then I'll close the recording, and then we can talk about the project due dates. Okay. Do you have any questions on the technical matter of today?
Sir, I wanted to ask something.
Yeah.
So we are talking about machine translation here. So
Yeah.
attention models are pretty good at machine translation. Are they good at something else other than
Oh,
this?
yeah, you know, we just saw an example of OpenAI's software, which is too good. Can generate all, you give it not just, give it some input sentence and ask it to generate new words. It can generate very plausible words which are not just syntactically correct. They're also meaningful to the what you just wrote. So it can be used to generate new text for anything you provide as input. So that is not a machine translation task. And we saw some of the examples. GPT has shown state-of-the-art performance in entailment, saying whether this following sentences follow from what was previously said. So is it logical to generate a summary of something? You can generate things that are truly follow-ups, and so those are examples. Generating new text or simple things like predicting the next few words when you're typing in Google Gmail. You're typing in Gmail a message, it's already predicting to you what the next word could be. And that is simply look ahead and generate some things, not just based on the previous word you typed, but also based on the gist of what all you wrote earlier on, who you are addressing letter to, and what is the subject matter, all that kind of thing. So there are all these, so you can ask the question, what is the application of natural language processing? And you name it. It could be Siri is able to doing speech recognition, and even when the sound is not very clear and garbled, it is able to make sense of what you might be saying and predicting all of that. So anything involving language, these BERT and are useful. And not only involving language, they have also gone off into vision and things like that. That's a different topic where you have to structure things differently. All right.
Okay.
Yeah. All right. Any other question? Okay, so I just wanted to give you a sense that there is a vast iceberg here called natural language processing, which is very sophisticated, involves all kinds of mathematics involved here, okay, and very powerful. And we have just explored a tip of the iceberg in terms of attention models. As you can imagine, this is a whole field of its own, a whole textbook of its own. And there is a textbook, I mentioned Jurafsky and Martin's book on this. So we may want to study those kinds of things. All right. So I will wrap up here, and we'll continue on Wednesday at the same time. Okay. I think I've stopped sharing the screen and live stream. Okay, all right, I stopped the live stream on Facebook. Okay, so we still have the Zoom meeting going on here. So we have 8 dozen or more students here. So I'll be putting this recording up. So in terms of the project, what I'd like to suggest, one or two students posted saying they still weren't able to finish project 3. What we'll do is, those who have finished project 3, please hand it in. The due date was the 15th, which is day after tomorrow, because the TAs have to look through all your work, and that takes time and so on. You've had plenty of time to do. If you have had proper access and so on, go ahead and submit it, and they'll start evaluating it. What about those who are handicapped, that they're in some remote area where there's no proper internet connection and all that? We will take that into account, and so you have to have a proper explanation to go along with it. and we will factor that in, so that we don't want to essentially stop any work on evaluating all your projects until you are all done. Every one of you is done. So it's just giving you feedback on your work. I think it's valuable to give you feedback while we are doing the work rather than some later point, which might be useless at that point. So please hand it in as we have scheduled, which is the 15th, which is the day after tomorrow. And if you are not able to, we will factor that in. And it's like when you're not well and you had a legitimate medical concern, instructors take that into account. Same, just like that. In this case, you're not unable to do your project because of your circumstance, and we'll factor that in. Okay. All right. We'll leave it like that for project 3, and project 4 again is mid May. We said. And of course, let's see what happens. The semester still be reopening in June or what? Who knows, right? So, okay. So that's all. Were there any other issues there? Okay, so we will conclude then. So stay safe till Wednesday, and hope to have you in class again on Wednesday at 11. And we'll move on to the next topic. I'm debating whether we've got to go into the next application, which is recommendation systems, or we move on to research topics such as autoencoder. Maybe I'm inclined to do one more topic, which is recommendation systems, because we have plenty of time, and we can do autoencoder after that. Okay, so most likely we'll begin on, I'll post it saying which lecture you need to look at if you want to do it ahead of time. All right, thank you all. Have a nice rest of the day.
Thank you, sir.
Yeah, bye.